In this video, we're going to look at early arms control methods, in particular the use of seismic waves and their detection. This was begun at the Massachusetts Institute of Technology with the spin-off, the Lincoln Laboratories. In 1957, they formed the GAG group. GAG doesn't mean, it means Geophysical Analysis Group. And the students, some of whom I know personally, they've retired, have spent their careers doing signal processing related to either detecting nuclear tests or finding new ways to explore for oil using seismic techniques. So why is seismic used for detection of nuclear tests? Well, we're not allowed, we, the world, that we can't have hydro tests. Water tests are out. There are treaties there that have been signed, and there are a lot of sensors and technology, for example, detecting submarines, so it would be very hard to hide a hydro test. The other is atmospheric. Atmospheric tests, of course, also would be monitored very easily. You've all heard about the volcanic eruptions that have been recorded using different sound gathering methods. There's also a treaty prohibiting atmospheric tests. That leaves what? Underground. And that's where most of the tests are done, for example, North Korea. Now, when underground test happens, it generates energy which squashes the rock elastically. So we have elastic waves, and we know here off the coast of Vancouver Island, we can have earthquakes. Earthquakes are elastic waves. Underground tests generate elastic waves. Quarry blasts generate elastic waves. Underground mine blasts generate elastic waves. So it means that we could use those detections of elastic waves, provided we can recognize them, to detect whether or not an underground nuclear test has occurred. Let's investigate this further. Supposing DPRK sets off an underground nuclear test. That will generate seismic waves. So here they go. And they come traveling through the Earth and hit a seismic station in Japan. You say, wow, well, we can record the occurrence of this wave from DPRK. Well, not really, because there's not enough information, because we could have an active fault somewhere here in the South Pacific that will also, at the same, for the same distance, also send a wave here at the same time. So there's not enough information with one station. So you say, okay, well, the first thing we have to do is put in more stations. You'd be absolutely right. So we can have a station in China. And we can have another station in South Korea. So just here. And then you see, with the 3 stations, we can hope to somehow triangulate and pinpoint the location of this event. Well, that's great in principle, but wait a minute, how do you know anything about what events look like? What's a characteristic of elastic waves? What's different between a nuclear test and an earthquake, a subject that's been studied for well over 60 years. To look at this further, we have to study what happens when a source in underground goes off, whether it's a fault, a mine blast, or a nuclear blast, and how these elastic waves are generated. So let's look at that in the next panel. Let's continue with seismic detection. We have a potential underground nuclear test from DPRK generating an elastic wave, a seismic wave that's sent from DPRK, and I cook up this station. It's in China, some distance away to the north, MDJ. Now, MDJ will record a seismic event. What we'd like to know is the distance between DPRK to MDJ, because that tells me if I'm sitting at MDJ, roughly where the seismic event happened. You have to be a little careful, as we indicated last time, that there is a whole set of possible locations that would have the same distance and traveling time of the wave. Like if this point here was about the same distance from DPRK as DPRK is from MDJ. So if I had a fault here that sent a wave up there, and this wave would take the same time as that, then of course I can't tell where it came from. All points on a circle centered about MDJ could possibly be locations. That's why we have to triangulate, as we talked about in the previous panel. But now we actually need to look at the seismic data itself and see how we can do timing measurements. Normally, timing measurements are you do like in a race. You start a stopwatch, race is over, stop the stopwatch, and then you can measure the time. But nobody's going to tell me when the race starts. That means when the event, the explosion occurs. I just measure a seismic recording. So what does that seismic recording look like? This is an idealized view of such a seismic recording. It consists of three main wave types in the recording. The first one is P, primary, primus, first. This is a push wave. Sometime later, a shear wave arrives. The shear wave is the one that causes all the damage in places like Turkey and Iran when there's an earthquake. It's a shake wave, a relative movement of the ground, if you like, sideways. And finally, what happens sometime later is the P wave, the push wave, like a wave going down a slinky, combines with the shear wave, and the combination of those motions at the surface of the ground causes the ground to actually go up and down like the ocean. And the particle motion on the ground goes forward and back, forward and back. These are the three main wave types that are recorded. How do we use these in discriminating between different events, location of events, and what's a nuclear test and what's an earthquake or a mine blast? So let's look at in more detail as how we can use this information to find out how far away the wave is from its source. In other words, how far is the location of the source that was recorded at the seismometer? In this case, how far away is the source from Chinese station MDJ to source location of a test set off by DPRK? An explosion, a nuclear explosion, is set off at DPRK station and is recorded at MDJ. This is what MDJ sees ideally. P wave coming in, push wave first. Fast wave. The shear wave is slower. It comes in later here. These times are clocked. Time is running here. So this comes in later, it's slower. It takes longer. And finally, the surface wave is the slowest, and it has lower frequencies and comes in late. Now, we need to find the distance from DPRK to MDJ. Let's assume, and this is not the case, but it's the simplest example, that the Earth's crust has a constant seismic velocity for both the P waves and the S waves. So, if the velocity is constant, we can calculate how far away we are by taking the velocity of the wave multiplied by the time it takes for the wave to travel from dprk to mdj. We don't know when it starts, that's the problem, so we can't set our stopwatch. But we can solve for the time it would take, given that we might know the distance, but we don't know the distance. But we can solve for that anyway. So the time it takes for a P wave to go from dprk to mdj is the distance between those two stations divided by the P wave speed. We do the same for the shear wave. The distance is the same from dprk to mdj, but the time will be longer because this is smaller than Vp. So this will come in, as we see from the recording, late. We can solve for the time it takes and write d equals Ts is equal to d divided by Vs. Same method here for both wave types. Well, now what do? We know that Ts is bigger than Tp, so we can subtract those two quantities. And that time difference, Ts minus Tp, can be measured. There it is. So if we can measure the onset of P really accurately and the onset of S in terms of their times, we can subtract the times. That time interval is exactly Ts minus Tp. That's measured. But also from the physics of this simplified Earth model, we have it here. So what's Ts? d over Vs. And from that we subtract Tp, which is d over Vp. Now what do we know? This is measured. And we know these, so we can solve for d. In order to do that, there's a bit of algebra. We have to factor out the d's. And if we do that, we get d into 1 over Vs minus 1 over Vp. That's the difference of two fractions. We know that difference. So that's a number. We measured this. So we have the change in time is equal to d times this. So if we divide both sides by this quantity here, we can solve for d. And that is absolutely fabulous. Directly from the records, we can get d, provided we know what the speeds are. Now, if you have some issues with the manipulations of the equations, in the linked video, I present an example using cars driving from Vancouver to Seattle at different speeds.